This is chapter 5, problem number 71. And this problem just asked for a force diagram, but we're going to go a little beyond that for what we're going to do. We can certainly do a force diagram. We can do it for the light here. So if we look at the traffic light, I'm going to put its force diagram over here. Notice we have the weight down, and T3 is up, and since it's not accelerating up or down, those are equal to each other. And so T3 is equal to 200 newtons. That's fine. What I'm more interested in is the force diagram really on this knot. That's what's going to allow me to figure out what T1 and T2 are, because we've already figured out that T3 is equal to 200 newtons. That's the tension from that point. Remember, tension always points away from the object. So while we're looking at the traffic light, the tension value points up. From this knot, the tension points down. And then we have T2 pointing this way and T1 pointing off in that direction. So this is T1 and T2. And again, there is no acceleration, and so we can set up an axis, right, like this, an X and Y axis, and say, hey, the sum of the forces, if we add them all up, in the X direction, that had better be 0. X. And the sum of the forces in the Y direction had also better be equal to 0, because that's equal to 0. So if we add up the forces, what we're really looking at is a bunch of component math. Sorry, there's the expression. So we're looking to get the components of all of these. So as we look at this, we can look at, first of all, we can recognize that this angle right in here, it's a little, I find it easier to use this angle, 49 degrees here, and this angle is, because again, this is a right triangle, so that would be 27 degrees, because 27 plus 63 gives me 90 degrees. Okay, so that's my setup. If I draw what's going on at this dot, then I've got T3 is down. I've got T2 sort of at this direction. T2, that's not the right angle. I'll try to do that a little more to scale. There's T2 with its angle right here of 27 degrees. And then I can realize it's got an X component, T2X, and a Y component, T2Y. And if we're careful about our trig, I'm just going to look at T2 for a minute, then we can say that, here, this is a little clearer, like this. This is T2, that angle is 27 degrees. The adjacent is the Y component, T2Y. So I can say that cosine of 27 degrees is equal to T2Y over T2. So T2Y is equal to tension number 2, cosine of 27 degrees. Then T2X is equal to T2 sine of 27 degrees. And then I can make the same arguments for T1, because T1 is out like this. And we've got 49 degrees here. This is T1. And then it's got an X component. Maybe made that a little bit too big, because T1X and T2X are the only X parts that we've got. And so what we have is that we've got T1X. T1 is in the negative direction, so minus T1X plus T2X must be equal to 0, because that's all that's going on in the X direction. And in the Y direction, we have T1Y plus T2Y. Those are both up, minus T3 is equal to 0. And T3 we know is 200 newtons. But we don't know what T1 and T2 are, but we can find those just by plugging in these kinds of values. So if we use the same logic that we have with this setup, the same SOHCAHTOA, then we're going to have, for T1, we're going to have minus T1, the x component is the opposite, so that's going to be sine of 49 degrees plus T2 sine of 27 degrees is equal to 0. That's for my x component. And for my y component, I'm going to have T1 cosine of 49 degrees plus T2 cosine of 27 degrees minus, I can move the 200 to the other side, equals 200 newtons. So I have two unknowns, T1 and T2, but I have two equations. So for the book problem, we're really sort of done once we drew the diagrams, but I wanted to show you how we could find more information because this problem could easily be extended in this way. And so at this point, we're just doing some algebra, okay? So from this point on is just math, okay? Now, to get a perfect score on something, you've got to get the math right. But if this is as far as you can get, then you're in pretty good shape already. You're showing me that you understand that a force diagram is telling you something about the acceleration. In this case, 0 acceleration. So if we set this up, we can solve, for example, for T1 in terms of T2 and then substitute that back in. So if I take this equation, I can take T1 to the other side, or I can say T2 sine of 27 degrees is equal to T1 sine of 49 degrees. So I'm just using this equation. I'm going to rewrite it. I'm going to say T1, I'm going to solve for T1 is equal to T2 sine of 27 degrees divided by sine of 49 degrees, right? That's just dividing both sides by the sine of 49 degrees. Once I have that, then I can substitute this expression right into my second equation. And that gives me T2 sine of 27 degrees over sine of 49 degrees times cosine, here, I'll keep the original color here, cosine of 49 degrees plus T2 cosine 27 degrees is equal to 200 newtons, okay? So I took this equation and I just substituted in for my T1 using this expression. And that's where we get to. So then I'm just typing things into my calculator. And when I put this all into my calculator, what I get is that I get this, all of this together is equal to 0.43996. This is equal to 0.89. So this I can write as T2 0.396 or 0.4 plus 0.89 is equal to 200. I add these two numbers together, gives me a 1.29. T2 times 1.29 is equal to 200 newtons. So T2, dividing by both sides by 1.29, I get about 155 newtons, if I plugged everything into my calculator correctly, which may be a big if. Once I have my T2, I can use this equation one more time, and I can plug in T2 now right here, right there, and multiply it by sine 27 over sine of 41 and get that T1 is equal to T2 sine of 27 over sine of 49 degrees. This is 155 newtons, so all of that going in, this gives me, when I put it in, I get about 93 newtons. And so that gives me the values. What their numbers are is really not that important. What's important is that you can see what the force diagrams give you. And then when we use this force diagram right here, this is really the key force diagram that was driving all of these equations, right? The x equation was T1x and T2x. The y equation had T2y and then, of course, T1y, right? T1y, and then minus our T3, which was this right here. And using that, we could then use some algebra to figure out, well, some trig as well, using SOHCAHTOA, but then some algebra to solve this problem.